liquid to gas. So if pressure increases on that liquid, then the temperature will increase. And if this happens, the boiling point will increase. So what does this tell us? Kitchens, especially kitchens that, big chefs that have to work with these massive amounts of foods and vegetables and pastas, they'll have something called a pressure cooker. And a pressure cooker takes water and it clamps it down and then it heats it all up. But because the pressure has increased inside that pressure cooker, they seal it all tight so nothing can get in or get out. And so since the pressure goes up, the temperature has to go up as well in order to boil. And if the temperature's gone up and it's boiling, then food cooks faster. That's the whole point of a pressure cooker. So this is an important one to know right here. At normal atmospheric pressure, normal boiling point of water is 100 degrees Celsius. I think I already addressed that. Okay, let's go on to the next one. Oopsie. Okay. All right, so here's vapor pressure and boiling. So you notice this compares two things. I have vapor pressure in torr, don't worry about that, just look at the numbers, and the temperature, which is degrees Celsius. So you notice temperature increases to the right and vapor pressure goes up. So I have three substances. Now, this is the stuff in beer and wine and stuff like that. That's ethyl alcohol and, water. So I know that as the temperature increases, water will boil at 100 degrees Celsius. This right here, this 760 that you see, this line, this is normal normal pressure that you feel, normal atmospheric pressure, okay? So you'll notice that the normal boiling point of water is 100 degrees Celsius at normal pressure, and that's the pressure you're probably feeling right now. Notice alcohol's a little less, and this diethyl ether, that's something you use in organic chemistry class, that's much less than that, okay? You'll also notice that the lines are not linear. They do curve, okay? So it does vary over an increasing amount of temperature. Okay, energy in boiling. The temperature of a boiling liquid and its resultant vapor are equal. Okay, so let's read that again. The temperature of a boiling liquid and its resultant vapor are equal. If we continue to apply heat, why doesn't the temperature of the water or the vapor increase as well? And the answer is this. Any additional energy applied is used to overcome the attractive forces. So the question that this slide is telling us is, why does water boil at 100 degrees Celsius and not more? Why can't I heat up water any hotter? Any additional energy that goes into that has to overcome the attractive forces, there. And in doing so, it can't get any hotter than 100 degrees. So the extra energy that goes in to break those attractive forces and thus increase the potential energy of particles, okay? So water will never boil anywhere hotter than 100 degrees Celsius, okay? But the energy in the steam is actually greater than that of the water because it has escaped, okay, which actually can do a little bit more damage to you. Okay, molar enthalpy of vaporization is defined as, now this symbol right here, this is a delta, it's a Greek letter. A delta means change in. Delta is defined as final conditions minus initial conditions. Final minus initial. So there's going to be like a little subtraction here on this stuff right here. So the molar enthalpy of vaporization. Now what is enthalpy? Enthalpy, I'm going to just, for you, it's just heat. And actually for anybody else, I tell them it's just fancy heat, and it just means that there has to be constant pressure. But molar enthalpy, you could almost call it molar heat of vaporization. It's the amount of heat needed to vaporize 1 mole of a liquid at, sorry about that, the liquid's boiling point at constant pressure. Now, this is specific to a liquid. I have to look this up in the back of the book, probably in your appendix, okay? So this is something we would have to reference. But the molar heat of vaporization or molar enthalpy of vaporization is, we can do calculations with this, with moles. So if I'm given the mass of something, I can convert to moles, and then I can find out this number by multiplying or dividing by the moles and find out how much heat it takes to get that amount of water or whatever liquid to vaporize, to enter the gas phase. Geez, what am I doing? Okay, freezing and melting. Obviously, they're two opposing forces, and this is the first thing that people don't realize. Freezing and melting happen at the same temperature, but for water, it's 0 degrees Celsius. Water freezes at 0, and it melts at 0. Now, that might sound obvious, but if I would ask the question, I guarantee some of you would have missed it. So freezing says you're going to take a liquid, and you're going to make a solid, and that solid, and the energy will have left. Notice the energy here is not in the liquid here. It has left. Okay, so I'm going to remove energy to freeze something. Freezing point is the temperature at which the solid and liquid are in equilibrium. So that's weird. Freezing point, we usually think it's when the liquid becomes a solid. Not true. Defined, it's when the solid and the liquid are at equilibrium, and I have to have something like a standard, and that's going to be 1 atmosphere. All right, so at freezing point, solid liquids have the same kinetic energy. Therefore, energy loss is in the form of potential energy. So when the liquid is changing to the solid, we have the same exact temperature. The solids and liquids are the same temperature. So where does the energy come from? It's the potential energy. You see, particles in the liquid phase are all moving around like crazy. But as they freeze, they start to form a regular pattern. And as they do this, they lose potential energy. So this potential energy that's lost is the energy that's lost when there is a phase change from a liquid to a solid, or freezing. Why? Again, as I mentioned down here, particles gain order and temperature stays constant at freezing point until all freezing is done, which is absolutely true. If I have water and ice at the same temperature, together in a glass, there will be 0 degrees Celsius for a long time until the ice is done melting, and then the temperature will eventually start to rise. And that's another thing we can prove. Melting is obviously the opposite. I have the solid. I have to add energy. So notice it's on the opposite side than it was up here to get the liquid. So melting, I have to add energy. Freezing, I have to take away energy. Okay, freezing and melting. Pure crystalline solids, freezing and melting occur at the same rate. So pure crystalline solids are anything that's ionic or ice or something like that. So you'll notice that freezing and melting occur at the same temperature. For water, it will be 0 degrees Celsius. At standard pressure, if the solid and liquid exist simultaneously, then the temperature of the system remains constant. I just made that point on the last slide, so that's another one that I bring up again. Again, if you have a glass of ice water, and here's your ice cubes in here, and this has been sitting around for a few minutes, and you take the temperature, it will say 0 degrees Celsius. And if you wait a half hour and you still have ice and water in here and you mix it up so it's all nice and good, it'll still say 0 degrees Celsius. If you wait another half hour, whatever time you want, and you still have ice in there, it's probably going to say 0 degrees Celsius. So temperature will change when either phase change is complete. So once all this ice is melted, the temperature will start to rise. An example, heat up, ice, water. Okay, that's what I just described. All right, next. Molar enthalpy of fusion. So we talked about the molar enthalpy of vaporization. Here's the molar enthalpy of fusion. In other words, this is the amount of heat required to melt. Before it was for the enthalpy of vaporization, it was the amount to vaporize. This is the amount of melting. And again, it's specific to each solid. I'm going to have to look this up in the back of your book. Okay? So, sublimation and deposition. Sublimation is anytime I take a solid, like dry ice, and it goes right to the vapor phase. It's that white powder, that white cloudy stuff you see. Now, what do? I got to put energy in to do this. So solid is order. This is disorder. I got to put in energy to get to the disorder. Deposition is the opposite of vaporization. This is the frost that you see on your car. So if there's water in the atmosphere and it drops below freezing, this is the frost, that rime frost that you have on your windshield in the morning. And this is where I have to have vapor. This is going to be a gas, like water vapor. And you have to remove energy. Notice energy is on this side. It's not over here. Therefore, I've removed that energy to get the solid. Okay? That's why it's on the right side of my chemical equation here. The last thing I wanted to talk about was a phase diagram. There's a lot going on in a phase diagram, and you should be able to interpret this. A phase diagram, you'll notice, has solid, liquids, and gases. Okay? Now, you'll notice that they're separated by these lines here. Any place along this line is a point of equilibrium. So along this line, there's an equilibrium between liquid and gas. Along this line, there's an equilibrium between solid and liquid. Here, between solid and gas. And you'll notice at this point, I have something called a triple point. The triple point is where all three phases are in equilibrium with each other. All three phases are in equilibrium, and it's true you can have this, and it's another experiment we can do. Another couple things. This is a phase diagram for water. It doesn't say that, but I'll tell you right now that it is. With water, you'll notice it's going to talk about the normal boiling point. It'll talk about the normal freezing point or melting point is what it says here. And then I have something here with a critical point. And the critical point is the highest pressure or temperature of which if I get above the critical point, I cannot increase the pressure anymore to get into the liquid phase. It becomes this supercritical fluid where it's kind of liquid, kind of gas. It's a real weird phase. Okay, and it's something you need tremendous pressure and temperature to deal with. And of course, you have the critical temperature. I just talked about the critical pressure. Then you have the critical temperature. So if I get up hotter, in this case water is 374 degrees, I cannot increase the temperature or pressure in order to get it back down to a solid or a liquid or a gas. Okay, that's it. That's what we have. If you guys have any questions on this, it's up to you. You have 1 week, or I don't know, in the future I'll probably have this. You have some time, I'll say that, to ask me any question. If you look at this the night before, you're probably not going to have enough time to ask me any question you have, and I definitely cannot address it in class. Study hard. Questions, don't call me, email me, or ask questions in class.